All right, so I'm going to go through this proof here as an example, but I really kind of more mean this to be more like a lesson on just how to do proofs in general. So as I get towards the end, I'm going to kind of add a little bit extra on there. So hopefully that'll be helpful and be more than just like okay, here's how you do this problem, but more like here's how you do proofs. Just because this is the thing I know from teaching this long enough that generally teachers teach this in a way that they just rehearse a already known proof, and that doesn't help the understanding what to think. That's the hard part about learning proofs, is it's all exercise, and teachers have lots of exercise in this, so they don't know how to turn that off and think, without knowing the answer. So I'm going to go through this one, put in a little bit extra, and then at the end I'll kind of talk more about that. So first thing, when you get a proof, a geometric proof, you're going to make a diagram, but if you make a diagram, recognize you're just doing that to help you see it. It doesn't help you prove anything. You can't actually say because this is parallel to that because you drew it that way. That's just because you drew it that way. You've got to prove it. You probably already know that. I'm just throwing that in there. And if they give you a diagram, don't trust it. So if something looks like a right angle, don't call it a right angle until you prove that. Or if two lines look parallel, you can't just say, oh, these two are parallel, so these two are parallel. You can't say it from the picture. So don't prove anything from the diagram, but the diagram is always helpful just to keep yourself straight as to where things are where, especially when you're dealing with these points. You got to figure out which points are which. I'll be honest, when I went through here, I messed up and got all the letters wrong and had to go back and just re-letter everything because I was thinking of it wrong in my head. I just had the wrong side of this as a parallelogram. So when I do a proof, especially a proof like this is one strategy. It's not the only strategy, but I like the strategy best because this helps you in that thinking through the problem and trying to figure out what's the next thing. It's easier to think backwards, to solve backwards, than it is to go forwards. Proving is when you're solving something, you're trying to manipulate it to get to a certain point. You're effectively doing the same thing. You're trying to get to a certain conclusion. Here, the conclusion, and so we're going to work our way backwards, and every statement we work backwards, then we know what we need to prove. So rather than thinking, okay, what do I need to do next? Instead, you know exactly what's next. Now the question is, how do I prove that? So it's proving, it's true proving because you're going backwards. So start at the end statement and work your way backwards, and then you'll hit points where you're like, oh, and that's given. Ta-da, you've reached pretty close to the beginning when you hit that point. But all the givens don't have to be at the first. Again, a lot of the examples you see, the given statements are up front, first reasons. It doesn't have to be that way. They can be thrown in wherever they are, whenever that point is needed. So in this case, they want us to prove that EKDJ is a parallelogram. We've drawn the picture. We got it right there. We know what we're looking for here. By definition, parallelogram, there's a couple definitions, but the one that you've already kind of caught on to and you're already using there is that opposite sides are parallel. So a parallelogram, quadrilateral with opposite sides that are parallel. So in this case, that would mean that EK is parallel to JD, and EJ is parallel to DK. So you've got those two opposite sides. That's what we need to prove. All right? So now we already have the last two statements of our proof. You already have it, the last two statements and the last two reasons. Last statement, last reason is EKGD is a parallelogram by definition. The next to last step is going to be EK is parallel to JD and EJ is parallel to KD. So that's your last two statements right there. So now we've just got to prove that. We've got to prove that one of those is parallel. I'm going to pick EK is parallel to JD just because it's first. There's no reason I could go with either one of these. It won't make a difference. So now the question I kind of ask myself, now that I know, okay, so I'm trying to prove that EK is parallel to JD, my question is, how do I prove that? Before I know what to do or how to prove that, unless I just kind of have an intuition or an understanding, I just ask myself, what do I already know about these? Like, what do I already know about EK or JD? Do I know anything about them already? In this case, I know that EK is parallel to BC because that was given. That was told. So that's just given statement there. That may be helpful. I don't know yet. Maybe that's where this is going. I'm just stating facts. There's a footnote there. Read the footnote. We also know that AD is parallel to BC. So I'm just kind of following it. Okay, so EK is parallel to BC because they told me that. That's just how it's constructed. And BC is parallel to AD because that's the other side of the parallelogram. We know that just because it's a parallelogram. So that right there is helpful. Like now, okay, that was one fact that led to another fact that I know is really helpful because AD is the same line as JD. Because JD is just 2 points on the line, the same line. So now I'm getting somewhere. Now I know where I'm going. Okay, so now I've got another point. So I can say because J is on AD, it's the same line. Okay, so I can say that. I could call this line, AJD, but I'm just going to say that to make it simple, JD is equal to AD. Like that line is the same line. The line segment isn't the same because they're different lengths, but the line is the same. So if BC is if AD is parallel to BC, then AD is also BC is also parallel to JD because it's the same line. So now we're one step closer. We're replacing the AD with JD, which is where we're trying to get to. We're trying to prove that JD is parallel to EK. And we already said that EK was parallel to BC. So then I can say, okay, if EK is parallel to BC, JD is parallel to BC. Lines that are parallel to the same line are parallel to one another. So that gives me EK is parallel to JD because they're both parallel to BC. In this right here, you probably want to read through this, maybe pause and just read through this the way I said it, because it may help, especially on the symbolic side. I can't really point out those things, so I'm just going to say, hey, read that and look at that. That may help you just understand how the statements come to be, how we write them. But effectively, now we're halfway done. Remember, we only had to prove 2 facts. We had to prove that EK is parallel to JD, and EJ, the left side there, is parallel to KD on the right side. So we're halfway done. Yay. Even better. We don't need to do all of that work over again. Proving that EJ is parallel to KD is exactly the same. It's exactly the same steps. We're just working vertically rather than horizontally. But it's the same steps, it's the same reasoning, it's the same everything. So mathematicians right now would just say, quote, similarly, we can deduce that EJ is parallel to KD, and just do a little, magic hand waving and move on. I don't know if that's rigorous enough for whoever's grading, or the professor or whatever. So I don't do that unless you can get away with it. But what we're going to do instead, just to make it as rigorous as possible here, we'll just make every statement include each pair. So it's going to be one statement that's including 2 separate facts talking about those opposite pairs. And that'll make the proof really short and sweet and look really nice. But that's the idea. The idea is we're really just going to use exactly the same reasoning we just did to say, okay, EK is parallel to BC, which is parallel to AD, which is parallel to JD, are the same as JD. Same game for the middle ones, the vertical ones, I mean. So now we just need to put it in order, write it down. So we went backwards. We worked our way all the way back to, we said those lines are parallel because it's a parallelogram. That was the last kind of step there. So that's where we start. Step 1, statement number 1, ABCD is parallelogram. That was given. And now we're going to do, again, each opposite side, we're going to state kind of at the same time. So BA is parallel to DC, and AD is parallel to BC. The opposite sides of a parallelogram are parallel. That's definition of a parallelogram. There's my reason. Reason number 2. Okay, 3, BA is parallel to EJ, and BC is parallel to EK. That was given. They told us that. So that's creating the inner part that we're trying to prove is a parallelogram. So that's a given statement. Notice I've got a given, I've got a definition, I've got a given. Just another example. I'm saying the given doesn't have to all happen at the beginning, even though a lot of the examples you see write it that way. BA, so going to the next one, we said that lines that are parallel to the same line are parallel to one another. So I'm just going to state that. BA is parallel to EJ, last statement, which is parallel to DC, which was from the second statement. And AD is parallel to EK, is parallel to BC. Again, back to the second statement. That lines are parallel to the same line to each other. There's the reason. Just that fact right there, I'm kind of taking for granted. There may be a theorem that shows that. You may have done something already, or it may be in the textbook. You can just kind of cite that theorem. It's not a named theorem, so I can't just like, oh, that's a name. But generally, people just understand that. So if you just say it, it's probably fine. But I would check your textbook first just to make sure that there's not a theorem you could cite there. Just depends. Next reason, so since they're all parallel to one another, we can just cut out the middleman, because the DC is the same thing as KD, BA. So we're saying I'm replacing the larger side with the smaller piece of the side that we talked about because they're the same line. So EJ is parallel to KD and EK is parallel to JD. And that's because K lies in the same line as DC. So we're replacing the DC with the smaller piece there. And J lies on the same line as AD. So again, we're replacing it with the smaller segment there. Lastly, so now we've proved it. We've proved that opposite sides are parallel. Reason number 6. So EK DJ is a parallelogram. And we're done. That's it in 6 steps. So you see, I worked backwards, and now I'm just reorganizing this into last to first order. Now, for a few more statements. This is it. That's done. Ta-da. But about proving. So here's the thing with proving. The hardest thing about it is learning how to understand what to think about. It's the thought process and the logic behind what happens next. It's an intuition. Knowing what's next is an intuition that you learn from exercise. It takes a lot of proofs to get that intuition to where you just kind of know what the next step is, and you can just kind of prove forwards, and it looks all nice like the teacher does. It takes a lot of exercise to get to that point. Watching a teacher work examples generally actually hinders learning that process because they're doing it based off that intuition they already have, or they already know the answer. So they're just rehearsing the answer. And there's those moments where they do something and you're like, well, that was magic. Where did you come up with that? How did you know to do that? Every math student has been there where you're like, where in the world did you get that? How did you know to do that? How would I know? I don't know that. That's the problem. Watching them do these actually makes this harder to learn. You can't show you what intuition is like, and they don't put in the effort or don't have the time to be able to deviate from the method that they rehearsed to show you the alternate paths that might lead to the right decision. So really, when it comes to proving stuff, it's messy, and that's gonna be my last slide. But here's this is an example. Like, I don't come from a background of parallel lines and stuff like that. I did a lot of stuff with triangles and trigonometry before I really got, where I was doing geometry. So I saw this and immediately thought, oh, parallel triangles, like there are parallel lines and triangles. They're similar triangles. Similar triangles have the same angles. If they have the same angles, then it's a parallelogram because the opposite angles, interior and exterior angles, are equal. So ta-da, like by transversal lines, it's a parallelogram. Everything I just said, you're like, well, where did you get that from? Again, that's intuition and background and stuff I've seen before. But see, that's just showing you like there's multiple different ways to do this. It just kind of, you have an idea and you work with that. Another idea is that, the opposite sides are equal length. The sides are the same length and they're parallel, and the angles, the opposite angles are equal. Sorry, angles are equal and sides are equal. That's a parallelogram. That's a different definition of a parallelogram. But if that's what you're thinking, that's probably where you're going to start. If you just did a problem that was talking about the sides of a parallelogram being the same length, the opposite sides, that's where your brain's going to be, and you're going to start there. And so you'd start a proof starting that. Okay, this is the end step. I need to prove this. So how do I prove that? And you would chase that rabbit, and then you'd find out, whoa, that's really hard to prove. Like, proving that these sides are equal is not easy. And in all of that, you'd probably get to the point to where you'd have to say, oh, these lines are parallel, and that makes it to where these points, oh, hold on, wait a second, that would be easier. I don't have to prove that these sides are equal. I can just prove that they're parallel, and that's good enough. And then you get to the path that we got on, that we proved. So see, like, a totally different idea could be a rabbit trail that you chase, and then eventually you come to the right idea. And you'd have to ditch that first part entirely in your final proof. And that's the way proofs work. They're messy. Like, there's missteps, there's dead ends. Sometimes you go in this loop and you come right back to where you started, and it's very redundant. You just work it out. You kind of work it out, you iron out the wrinkles, and then you look for shorter ways once you're done. Once you finish it, once you get there, then you're like, okay, now I'm going to look for the places I messed up, or the places where, oh, I didn't need to prove that at all. That didn't matter. I could have just done this instead. So that's just again, sorry, bell rang. So that is the difference there. It just kind of changes with that one. I once did a proof. It was pages long, and then I had to present it at a conference, and so I'm presenting what I found. And when I got to the proof part, I was like, I really don't want to show them this because of how messy it is. It's just a whole bunch of algebra. It's pages of algebra. And so I zoomed out on the page of algebra and pointed at it and said, because algebra, and then went to the next slide because I just really didn't want to show that part because of how messy it was. But the entire room, which is mostly professors, like, started laughing because they were like, yeah, that's just like us. Like, I kind of broke the fourth wall. Like, they get it. They've been there. And I still won an award for that presentation. Like, they all got it. They understood that this is just the way proofs work. They're messy. They don't make sense. The logic there kind of comes to you in pieces, and then when you look at the whole picture, then you're like, oh, now I get it. So just some encouragement there when you're working through proofs to just kind of try things. Like, stop, don't try to mimic the professor who just knows. Just figure it out, and then go back and make it better, make it cleaner. That's the way to go through it. And watching them do more examples will possibly make this harder to learn. You just kind of figure it out and then keep going. All right, hope that's helpful. I'll send this video to you soon there. If you're looking at this and going, oh, that's 18 minutes long, just turn off the sound, read through all the slides first, and then decide whether you want to actually listen to the rest of this. Yeah, I know I'm telling you this in too late. So thank you for listening.